Good afternoon. I'm Saritha Kumari, Assistant Professor, EEE Department, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Today, my topic is voltage distribution over a string and problems based on that. So, this topic is uh, in the insulators, right? Second module. So, it is mapped to course outcome 2. It is 2. I'm sorry, it's 2. Course outcome 2. And so it's about the insulators and also the efficiency in that, calculating efficiency. And then the other thing, as I mentioned yesterday in my last lecture, sag and tension parameters. So today the topic is voltage distribution, right? So voltage or potential distribution over a string, suspension string of insulators. So here we know what is meant by basically suspension insulator. So this is a type of insulator. Um, so where number of porcelain discs are connected in series by metal links in the form of a string, right? So that is nothing but suspension type insulator, right? A number of porcelain discs are connected in series by metal links in the form of a string. So that is called suspension. Okay, suspension insulator. You can see on the left side, the first picture of that, there are three porcelain discs. Okay, 1, 2, 3. So they are connected in series, right? They are connected in series by a metal link between them. Okay, so they join. So any two porcelain discs are joined by a metal link like this. So and at the end the conductor is passing, right? At the end the conductor is passing, uh, and it is suspended from the cross arm. So this is a cross arm. On the other side there is a pole supporting tower, right? It may be a pole or tower. So this is how the arrangement of this suspension insulator. In my last lecture also, I have shown how it looks like, right? So okay, so this is a cross arm, and on the other side there is a on the other side there is a pole. There is a support. Okay, so this is all how the arrangement. And on the down, the conductor is passing, transmission line conductor is passing. Okay, and now here we can see three discs are there, and three porcelain discs are there. If V is a applied voltage, let us say V is a applied voltage of this of the system. So the voltage appears across the total string. Now, because there are three metal links, the total voltage is divided into three parts, right? V1, V2, V3, right? The total voltage, the operating voltage V is divided into three parts. Okay, V1, V2, V3. Now, the first figure 1, let us say, is redrawn as like this figure 2, because we know that porcelain disc is nothing but a insulator, right? So uh, between the, we know that it represented as a capacitor, right? Insulator means it is a dielectric material, we can say. So on the both sides there is a metal link. So between two metallic points, metallic plates, there is a porcelain disc is there, right? That means dielectric, we say. So that means each porcelain disc is represented with a capacitor. Okay, so one capacitor, one. Okay, this is another capacitor, and the third one also another capacitor. So and because they are in the series, so we know that basically the same current flows to the each capacitor. Let us say that I. Okay, same current flows through the capacitors, right? So the current is in the system is let us say I, capital I, is flowing from the conductor to the cross arm. Now because the current flowing through the three capacitors is same, and the total voltage applied is V, and the each disc is of the same type. So the capacitance, okay, of the each unit is same, right? Current is same because they are in series. So same current flows through each unit, each disk, and because we know each disk is of the same material, same type, so each one is represented with the same capacitor. Let us say C. Okay, let us say C. So all are same. So current flowing through them also same. So the total voltage is divided into three parts. So here that is given as in terms of V as V by 3, right? V by 3, okay, is the voltage across the first unit. Then second V by 3, voltage across the second unit. Okay, then V by 3 is the last V by 3 is the voltage across the last unit, bottom unit, right? So this is how like voltage distribution over a string, okay, suspension string, insulator string. But but here, um, in addition to this C, capacitance C, this is called self capacitance, okay. So this is called self capacitance of the each unit. In addition to this, there is a another capacitance comes into picture. That capacitance formed between the each metal link and the pole supporting support. Okay, whatever is there, supporting tower or supporting pole. Okay, so that capacitance is comes into that capacitor comes into the picture between the each metal link and support, right? So and that capacitor is called here shunt capacitance, which is denoted with C1, which is denoted with C1. Okay, now so for first unit, top unit, okay, so this is a C1 shown like this, and current flowing through the different parts. Okay, first we know that in the top unit, in the series path, first is capital I1. Okay, then the current flowing in the shunt path, okay, through the C1 is, let us say, small I1, small, okay, top unit, okay, shunt capacitance current is small I1. Next, the current flowing into the second unit, okay, so the current is due to self capacitance is capital I2, and current flowing in the shunt capacitance second C1 is, let us say, small I2. Then current flowing through the bottom unit due to self capacitance is capital I3, and current flowing through bottom shunt capacitance is small I3. Okay, so this is how the, because of the shunt capacitance, okay, which comes into the picture, okay, and because of this the currents, okay, because capacitance presence, there is a some current is drawn, right, by that shunt path, shunt capacitance. So because of this mainly the voltages across the units, even though the three units, okay, we have taken here three metallic discs, three discs, right? So three porcelain discs, okay, the voltage distribution among them is not uniform, it is not the same, okay, because of this shunt capacitances, okay. So the voltages across the voltage distribution across the units is given by across the top unit V1, next unit V2, then the here third unit, that is a bottom unit, okay, that is V3. So That is the reason, okay, why the voltage distribution is not uniform over a suspension insulator string, because of the mainly shunt capacitance, because of the shunt capacitance present in the system. Now, uh, because of this non-uniform voltage distribution, the efficiency, okay, will get low, right? String efficiency, we want to, I mean, string efficiency we want to know. So we wanted it to be good value, right? Right, 100% for ideal case. Now see that how they are defining the string efficiency. The ratio of voltage across the whole string, ratio of voltage across the whole string to the product of the number of discs and the voltage across the disc nearest to the conductor, nearest to the conductor is known as string efficiency, right? So that is how the string efficiency is defined. Okay, ratio of voltage across the whole string, right, to the product of number of discs and the voltage across the nearest conductor, nearest disc, which is voltage across the disc nearest to the conductor. So expression, okay, this is the expression in the numerator, total voltage, okay, voltage across the whole string divided by down n into n is small, n is nothing but number of discs in the in the string, and voltage across the disc that is nearest to the conductor. Now see the mathematical calculation to get that string efficiency. This is taken from the my reference to now this mathematical derivation. So here let us diagram is shown with the three, okay, discs, three units, okay, so 1 2 3, right? So accordingly, as we know already how the current distributions are shown, okay, current through the current through the self capacitance are capital I, capital I1, capital I2, capital I3. Currents through the shunt capacitances, okay, C1 is small I1, small I2, small I3, right? And the voltages across the units, top unit V1, next unit V2, next last unit V3. Now, see that finally we want to calculate the string efficiency. So, how to calculate that? So, they have shown the each node. Okay. So, here in this diagram, there are two nodes. There are two nodes. Okay. First one top, at the top unit, the common point, right, is one node which is capital A, which is shown with capital A. Next unit corresponding to next unit, the common node is the common point is uh, this point. Okay. So that is a node B, let us say, okay, and the last one node C, okay, that is a node C. Now, so first at node A, look at the left side, applying Kirchhoff's current law at node A. Okay, so applying Kirchhoff's current law at node A. So what is the incoming current? Capital I2. Okay, is equal to leaving currents are capital I1 plus small I1. Right? Capital I2 is equal to capital I1 plus small I1. Now, so that is what it is written. Now, the currents are written in terms of the voltage and also the capacitance, corresponding capacitance. So, I2 is given by what? Okay, voltage across that is V2 multiplied with omega C, right? Omega C. So, that is what here it is mentioned. Okay, I2 is given by V2 into omega C. And what is I1? V1 into omega c. Next, what is small I1? V1 into j omega, sorry, I1 is equal, small I1 is equal to V1 into omega C1, right? So here, how you know the voltage across this C1? So this is nothing but the voltage across this point and the voltage across this point and this point. This point is same as this point, right? So what is the voltage across these 2 points? V1. That's why that is written as V1 into omega C1. So now cancel the similar terms on both sides. So we cancel before cancelling the common term, write down C1, okay, in terms of C. So to get the relation between C1 and C, there is a factor they defined, okay, that is there in the picture, small K, which is defined as the ratio of shunt capacitance to self capacitance, okay. K, which is defined as ratio of shunt capacitance to self capacitance. That means shunt capacitance is a fraction of the self capacitance. Shunt capacitance is a fraction of the, okay, self capacitance. That is the meaning. So this K value um, always less than 1, okay. So that is a meaning. K value is always less than the 1. Now, so here, so that's why this K1 is written as in terms of C as K into C, okay, K into C, okay. Suppose we have a problem in based on this, they will give us the data, okay, they will give the data, the value of C and C1, or they will give the value of K directly, okay, that fraction value they will give, okay, to solve the problem and to finally calculate the string efficiency. So here this C1 is written in terms of C as K into C. Now cancel on both sides omega C. So finally we have this expression, okay. V2 is equal to V1 into 1 plus K. Next, similarly, apply KCL at node B. So at node B, what are the incoming currents? Capital I3 is equal to leaving currents capital I2 plus small I2. So that is what written. And what is I3? It is given by V3 into omega C, and V2, capital I2 is V2 into omega C, and this small I2 is given by, okay, look here, V1 plus V2, because the voltage between the this point and this point is what, how much this point means, okay, this point and this point, right? So this point and this point means this point is same as this. So voltage available between these two is given by V1 plus V2. So that's why V1 plus V2 into omega C1. Okay. Now again the same manner, replace C1 in terms of Kc. So this is what, and finally simplify the equation, cancel the similar term omega C on both sides. Finally we will get V2 plus V1 plus V2 into K. But we know that what is V2, right? What is V2? So V2 is V1 into 1 plus K. So substitute finally V3 is written only in terms of V1, okay, and K. So what finally we want to calculate the efficiency, okay. So now voltage between conductor and earth, that means total V is given by sum of the V1, V2, V3, right? So already we have V2 in terms of V1, V3 also in terms of V1 from the previous. Okay, so substituted V2 is V1 into 1 plus K, V3 is V1 into 1 plus K plus K square. So finally V1 is common taken. So V is equal to V1 into 1 plus K into 3 plus K. Now So from the expressions 1, 2, 3. Okay. So what are the equations 1, 2, 3? This is the first equation. Okay. And this is the second equation. Okay. Second. And this is the third. Okay. So finally all we have, it is written as, so what is what is equation 1? V2 is equal to V1 into 1 plus K. And V3 is V1 into 1 plus K plus 1 plus 3K plus K square. Right? Right. So this is 1, this is 2, this is 3. Now, so from 1 to 3, okay. So V1 by 1 is equal to V2 by, okay. So from the first expression, we can write V2 by 1 plus K is equal to V1, right? V2 by 1 plus K is equal to, from this, V2 by V1 1 plus K is equal to V1, right? Then V3 by V1 is equal to, from the second expression, V3 by 1 plus 3K plus K square is equal to V1. Next, from the expression 3, V by 1 plus K into 3 plus K equal to V1. So that is what? Okay. Now, the voltage across the top unit, that is V1, is given by, from this, okay, V by, okay, 1 plus K into 3K. Okay. Voltage across the top unit, V1 is given by V by 1 plus K into 3 plus K. Next, similarly, V2 is given by, okay, V into 1 plus Ky. Okay. V2 is equal to, because we have obtained the V1, right? Sorry. So V1 already we have obtained from the total voltage V. Okay. V by 1, from this we already obtained the V1 value. So they are using simply that to calculate the remaining V2 and V3. So finally, anyway, V1, V2, V3 are calculated. So that means depending upon the given data, if they have given the total voltage V, okay, so we can calculate like this, V1, V2, V3. Okay, K value also given. Now, finally, string efficiency, percentage string efficiency. We know that voltage across the string, whole string. Okay, V by N means here 3 is next to last one, voltage across the disk near to the conductor. That is nothing but V3, right? What is that disk that is near to the conductor? That is a V3. Third car, bottom unit. Voltage across that is V3. Now, see that a problem we have. So, this is a problem in a 33 kV. In a 33 kV overhead line, there are 3 units in the string of insulators. Okay, line operating voltage is given 33, and they mentioned how many units? 3 units. And if the capacitance between the each insulator pin and the earth is, they have given that capacitance between the each insulator and the earth. So they have given capacitance between the insulator pin and earth. Earth means what? They have given the side capacitance. Okay, they have given shunt capacitance. Okay, is 11% of self. So that means they have given C1 by C. C1 by C is equal to 11%. They have given 11%. They have given. So 0.11. Fine. First bit, distribution of the voltage over 3 insulators. Next, second bit, efficiency. Okay, so draw the diagram. Already we know what is this diagram. Okay, so because they mentioned 3 units, so that's what it is shown. 3, okay, parts, 3 sections. Okay, and then the self capacitance is also shown C1, but it is written in terms of K and C, right? because we know that K is nothing but C1 by C, right? So C1 is nothing but Kc. Okay, so that is what they have given. So now look at the solution. K is equal to C1 by C, which is equal to 0.11 given, and voltage across the string they have given 33 33 kV line. That means it is always line value. Given data is always line voltage. So because if they didn't say line voltage or phase voltage, so if not given means it is always line voltage. So that's why they calculated phase voltage of that, because the voltage across the total string is between the conductor and the earth. So this V is nothing but per phase voltage we want to put it in the solution. So 33 kV by root 3 gives the 19.06 kilovolts. Now at junction A, first, okay, junction A apply KCL. So capital I2 is equal to capital I1 plus small I1. So V2 omega C equal to V1 omega C plus V1 K omega C. So this is nothing but C1, right? So they have directly written in terms of, okay, K and C. So now V2 is equal to cancel omega C on both sides. V2 is equal to V1 into 1 plus K, which is nothing but K is 0.11. So V2 value is 1.11 volts. 1.11 V1. Similarly at junction B, okay, this junction same, apply KCL. Capital I3 is equal to capital I2 plus small I2. Capital I3 is given by V3 into omega C, and capital I2 V2 into omega C. Small I2 is V1 plus V2 into omega K omega C, right? It is directly written because, okay, in terms of K and C. So substitute, and here already we know that V2 is 1 point in terms of V1, 1.11 V1. So substituted that is here. So V3 is given only in terms of V1, 1.342 V1. So finally, the coming to the calculation of first bit voltage across the total string. Okay, first bit they asked to calculate voltage across the each unit. So for that, we can solve like this, right? V is equal to V1 plus V2 plus V3, because V2 and V3 we know in terms of V1, right? So substituted that. So V2 is equal, V is equal to V1 plus 1.11 V1 plus 1.342 V1. So from that, V is equal to 3.452 V1. So from that, V1 is this V is given by, we know, system voltage, operating voltage across the conductor and the earth given. Okay, 19.05 kilovolts, right? So which is equal to 3.452 V1. So V1 is given by that 19.05 by 3.452. So which is 5.52 kilovolts. Similarly, voltage across middle unit V2 is given by, because we know that V2 in terms of V1, 1.11 V1. So V1 already calculated, okay, 5.52 into that 1.11 gives the V2 value. So similarly, V3 also calculated in the same manner. Now, string efficiency, it is string efficiency is given as voltage across the whole string, that is 19.05 by 3 into what is the voltage across the disk that is near to the conductor V3, right? 7.4, that is obtained as 7.4. So percentage efficiency they want to calculate, which is obtained as 85.8. So this problem also taken from reference to, okay. So that's why, okay, answer is 85.8%. Next, so these are my references, okay. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.